associate members of Space Engineers Association. Good evening to all. Today we have gathered here virtually to celebrate National Science Day, instituted to honor of one of our greatest scientists, Dr. C.V. Raman, and his remarkable contribution to the realm of science through his discovery of the Raman effect. It is my honor to welcome all of you on this auspicious day and share this space with you all. The theme of National Science Day 2022 is Integrated Approach in Science and Technology for a Sustainable Future, and we have an eminent speaker today to share his insights with us. Our speaker of the day is Dr. Tarun Souradeep, Director of Raman Research Institute, which is one of India's premier science research units. Dr. Tarun Souradeep is an internationally known gravitational wave physicist and a lead player in India's contribution to the Laser Interferometer Gravitational Wave Observatory called LIGO. Today's topic of today's presentation is CMB Bhārat, which is a project for comprehensive next generation cosmic microwave background mission with international collaboration. I extend a warm welcome to you, sir, on my personal behalf as well as on behalf of Space Engineers Association. Let me also take this opportunity to welcome all of you. I would like to conclude quoting the wise words of Margaret Beckett: humankind has the science and technology to destroy itself or to provide prosperity for all. But while science offers us these opportunities, science will not make that choice for us. Only the moral power of a world acting as a community can. Unquote. Let us drive our scientific efforts to build sustainable futures. Once again, thanking you all. Thank you.
Sir, I request our Dr. Rajshekhar, team leader for the technical board, to introduce the speaker to the audience today. So, Rajshekhar. Sir, you are not audible.
Muted it.
Sir, you are not audible. Rajshekhar, sir. Rajshekhar, sir, you are not audible. Please unmute yourself.
He had his BTech from IIT Kanpur and in mechanical engineering.
Mr. Rajshekhar, can you start from beginning? Initially, we could not hear you.
Yeah, okay. Good evening, all. And a special good evening to our. Am I audible?
You are audible now, sir.
Yes.
Yeah, I don't think I'll mute my video camera so that the bandwidth is available. Okay. Good evening, all. Special welcome and good evening to our speaker of the day, Professor Tarun Souradeep, Director of the Raman Research Institute. It's a glamorous biodata. He had a BTech in mechanical engineering from IIT Kanpur. Subsequently, he had a PhD from Indira University Center for Astronomy and Astrophysics, famously known as IUCAA, Pune. He held very, very glamorous positions also. He was senior professor at IUCAA, and subsequently he was professor and chair of the Department of Physics at IISER, Pune. Then he took over as a director of Raman Research Institute, the very same institute founded by Sir C.V. Raman. I have been there twice to meet Professor G. Srinivasan. Then he had very, very great awards too. He's the chief spokesperson for the Laser Interferometer Gravitational Wave Observatory India, LIGO India. Member secretary of the Scientific Management Board together with Professor Bala Iyer. He's a recipient of various awards like DST Swarna Jayanti Award. Then he's a member and a Special Breakthrough Prize in the year 2016 and a Grubber Cosmology Prize in 2016 as well as 2018. He's a fellow of the National Academy of Sciences and the Indian Academy of Sciences. Once again, Indian Academy of Sciences was founded by Sir C.V. Raman himself. His election to the fellowship of the International Society on General Relativity and Gravitation. That's a great place. Kudos to you, sir. And we welcome you on behalf of Space Engineers Association. We are ready to hear you. The floor is yours, sir. Please come.
Thank you so much for the kind introduction, Dr. Rajshekhar and Dr. Satish Kumar, and of course to Sendil for the invitation. So I'll just share my slides. Hope you can see them.
Yes, sir, the slides are visible.
Okay, excellent. So the topic of my talk today is a new adventure that I am, hoping we will all embark on. So LIGO India certainly is something that I'm still involved with, and we proposed this as a project in 2011 to the Mega Science Committee of the Planning Commission then, and it's a project underway. And that, of course, as you know, in 2016, the first detection of gravitational waves was announced by the LIGO collaboration. And many of us, as part of the LIGO India contribution to LIGO international collaboration, were co-authors on that work. And, it's been a great, privilege to be part of this frontier science. But if you listen to the Nobel lectures of three of the scientists for LIGO who were awarded the Nobel Prize, two of them, Professor Kip Thorne and Professor Rainer Weiss, both mentioned in the Nobel lecture the next big thing they're looking forward to, and that is gravitational waves from the origin of the universe. Okay, and it's a very unique thing for me because this bears very close relation to two areas of science that I have been personally very interested in. One of my earliest papers, in fact, the earliest paper was on the signature of gravitational waves in the cosmic microwave background, way back in 1992, when Kobe first discovered these fluctuations in the microwave background. And so it was a really exciting time when ISRO announced and made an announcement of opportunity for space missions, and we put in a proposal which was from an Indian cosmology consortium, which we called CMB Bhārat, and proposed a mission which was early exploration of cosmic history and origins. But somehow the name CMB Bhārat seems to have stuck with it, so we call it also the CMB Bhārat mission. And I feel that this is the most appropriate forum in which I could, voice what we as scientists wish to do together with ISRO. And I hope you pay attention to what we have proposed and what kind of challenges we would like to meet on the way there. So let me give you a context, because cosmology is not something that you would be always thinking about. But I think mankind has always wondered about the cosmos, because if we look out in a beautiful location like this and the Milky Way reflected in the lake here, it is a splendor that always people want to know, where did this origin? Where are we in the universe? And that's one of the deepest questions that mankind has ever posed. And it has been the oldest question, as old as humanity. So what we are seeing in this picture are largely stars in our own galaxy. The Milky Way is the galaxy where our sun is just one of the ordinary stars, and we are a planet going around it. But the Milky Way itself is just one of many, many galaxies. So if you look away from the plane of the Milky Way, where there are too many stars, and look at a dark part of the sky and peer at it with, again, some things based on space. So this is the Hubble Space Telescope, which looked at a part of the sky for a long period, took a long exposure, and produce what is called the Hubble Deep Field. Now, every spot of light that you see in here is actually a distant galaxy. Okay, some of the galaxies are obviously looking like galaxies, which you can see spiral arms and things like that. But even these small splotches here are actually galaxies. They look like undefined splotches because you are seeing galaxies so far away that you are seeing them when they are just forming. This is almost the beginning of formation of galaxies that we are peering back into. And we know that the universe is full of galaxies. And in the cosmological era, arena, a basic unit for how we look at cosmology is a galaxy. Galaxy is like a tracer particle, just like, when I'm looking at airflow in a room, I don't worry about every molecule. They're just tracing, you put some dust, this dust is tracing the airflow. But the galaxy itself is a very rich structure. It has 100 billion stars. It stretches, hundreds of 100,000, light years in size. And this is something where it shows you, if you were to fly through the universe, as many science fiction stories would show you, Star Trek or something, this is what you would see. The universe is full of galaxies, and the galaxies are organized in a very interesting structure. And this is the universe we try to understand as cosmologists. Okay. And this looks like a very complicated universe, but we have a very simple way to address this complexity. If you look at galaxies projected back on the sky, what you can infer is the broad distribution, average distribution of galaxies over large patches is almost the same in any direction of the sky. So it's fair to say that in the universe, the distribution of matter, which is seen as galaxies, is isotropic. It's the same all around us. And if we believe we don't inhabit a special place in the universe, then it must be so around any distant galaxy. Observer in any distant galaxy would find isotropic distribution of galaxies around it, which lends credit to the simple model of cosmology that came up even in the 1920s. And that is smooth expanding cosmos. Okay, and that itself was so radical that Einstein, when he first realized that his gravitation led to a cosmology which was evolving, tried his best to keep it static. Okay, but nature determines what it is. So Einstein's general relativity, which was very new in 1915, applied to a uniform distribution of matter on cosmic scales, led to a smooth expanding universe. So what's happening there is you can imagine the universe to be three-dimensional surfaces stacked up, just like you can look at a ream of paper and each sheet is stacked on top of each other. You can label each page with a page number, which will be the time. Similarly, the universe can be thought of as a spatial hypersurface, three-dimensional hypersurface evolving in time. And what is happening due to the dynamic nature of space-time in the gravitational context, the space-time is expanding. It's like a membrane or fabric that keeps expanding with time. So galaxies, although they are pegged to the same point on the fabric, seem to be going apart because the fabric itself is expanding in time. And so that is what is shown in this animation, that you can see the galaxies are moving apart. And we built cosmology with very basic physics, but in this expanding arena. Okay, I wanted to just emphasize that there's nothing exotic. It's the same physics that you use in your lab, or even when you are looking at, gas dynamics or plasmas. It's the same story here. And that leads to a very, very, simple model, but very, very important, that if we know the current composition of the universe in terms of amount of matter that clusters under gravity and amount of matter that does not cluster in gravity, and know the expansion rate at this time, then you can say what the universe did in the past in terms of its expansion and what it will do in the future. And I'm pointing to the red curve because our current observations have picked a curve like this to be what the universe is evolving on. This is the track on which it could have evolved on any of these tracks, but we know now that it is evolving on this track. Okay. So one of the biggest support for this whole model that the universe is isotropic around us. I showed it in terms of galaxies projected in the sky, but comes from the dominant radiation component in the universe. So in 1965, very serendipitously, it was discovered that we are surrounded by a radiation bath, which seems to be isotropic. At that time, you didn't see any anisotropy, but in 1992, we detected anisotropy at the level of 10 parts per million, which was a big breakthrough of the Cosmic Background Explorer, yet another space mission. And this completely, is the dominant radiation content. This determines all the radiation in the universe. You have gamma ray sources, you have X-ray sources and everything. But the cosmic microwave background accounts for everything, every radiation in the universe. It's also a Planck spectrum, so a black body spectrum at a temperature which is now measured to the third decimal point. Okay, and this lends support to this idea that the universe started from a hot, dense phase and is expanding and cooling. The radiation is cooling with the expansion factor. Okay. Now, observationally, the thing to imagine is the following. Where is this microwave background coming from? We are here and now. As I look out to the distant universe, since no information can travel faster than the speed of light, we are looking at things back in the past. In fact, it's interesting to think that when we see the sun every morning, every time we look at it, we are looking at it as it was 8 minutes ago. So if something dramatic happens on the sun, like a solar flare takes off, we will see it in the only 8 minutes later. But for a distant galaxy, it could be billions of years before the light and the signal comes to us. So for example, the LIGO detection, first detection was from a galaxy where the light traveled for 1 billion years and came to us. If we go far, they hit a surface around us, which is pure plasma, because you have gone to a universe which is way back in time, where now we are 14 billion years old. This is a universe which is only 500,000 years old, and it is hot and so dense that all the hydrogen and helium is in plasma form. And as you all know very well as engineers in this thing, you can't peer back through a plasma. The plasma has such scattering that you can't get coherent information. So this is the boundary of how far you can peer with electromagnetic waves in the universe, right? This plasma surface. And if you were to take a thermometer and measure the temperature here, it's 3,300 Kelvin at the plasma. But because of the expansion of the universe, we see it as a 3 Kelvin bath, like the 2.7276 kind of number that I quoted earlier. And that is the cosmic microwave background. So cosmic microwave background is the relic of the hot era of the universe, as it was when it was only 0.5 mega years. Just to set the scale, this is like if you are looking at a 100-year-old person and I show you a picture of him or her at the age of 1 day, right? So we are looking at the infant universe. Okay, but this cosmic microwave background allows you to probe the universe so early in its time, and also over distances, enormous distances, 43 billion light years. So it traverses everything in the observable universe before it comes to you. So this is a rich probe of what has happened in the universe, in its history, as well as in its extent. And what should it see? So we see an isotropic bath, which tells you that by and large, the universe was isotropic and homogeneous at that point, at the age of 0.5 million years, to the level of 10 parts per million. But we also see fluctuations in it, which are the seed for the galaxy distribution that I flew through in the universe. And any volume of the universe, typically the galaxies are organized in this rich structure. But this rich structure that you see in the density field is seeded, and the seeds of that is seen in the cosmic microwave background. So this is the picture you should look at. So we are here and now, we are looking back at this plasma screen. And from 92 onwards, 1990, when COVID went up, we first started seeing some structures in the intensity distribution of this background. Till then, we only saw a smooth background. We didn't have the sensitivity to see these small fluctuations at tens of microkelvin. And this is immensely important. As I told you, these are precursors of everything that you see now, of these galaxies and structures that you see now. And that is what has allowed us to pin down what is our cosmological model. So it's been an enormous boost in the last 30 years to have these results from COBE at 1992, improved over generations of space missions, which I'll talk about. But there's another aspect to it, which is yet to open up. The question to ask is what created the perturbations in the first place? And for that, we know that it has to be some very early universe physics which imprinted these density perturbations and also in parallel imprinted some gravitational wave signal that is seen in this plasma, right? That is recorded in the plasma. We have to have the sensitive enough instruments to see both of them. And we have done a lot along the 3 decades. So just to recap, it's a 3 Kelvin bath on which we detected in 1992 a fluctuation at 70 microkelvin RMS fluctuations. As engineers, you would realize that this requires considerable technology improvement from the first time you detected a 3 Kelvin bath to detecting 70 microkelvin fluctuations. Okay, and then, sorry, I'll just mute my phone. So COBE was only the first generation, and it saw these fluctuations with a very coarse resolution. And then in the next decade, 2001 to 10, was dominated by a second spacecraft from second mission from NASA. COBE was from NASA. WMAP, Wilkinson Microwave Anisotrope, was also NASA. And that mapped the same fluctuations, but at much better angular resolution. You can see it's the same map, but seen with better eyesight. And the third decade, somewhere like 2009 to 2011, was Planck observations, but the final results came out in 2018. That really mapped out the sky at the highest resolution possible to extract science and made remarkable inferences, right? Then I will tell you why we are proposing CMB Bhārat, which is the next generation space mission. I should also mention that there's been huge improvement to the sensitivity. Planck sensitivity is 25 times better than WMAP, and Planck resolution is 3 times better than WMAP. If you compare to the first generation, it's a factor of 1,000 in sensitivity and 100 in resolution, angular resolution. And there have been lots of efforts from the ground also, ground experiments. What Planck produced is a full sky map of this plasma surface, the intensity fluctuations at the level of, say, in this map, the hottest spot is 300 microkelvin and the coldest spot is minus 300 microkelvin above the mean. Mean has been taken out, of course. The mean is 2.7 Kelvin. And then this is essentially a blueprint of the structures that later formed in the universe. And it's really mind-boggling that we see the initial seed perturbations from which everything that we see in the universe, galaxies, stars in them, and the planets, everything arose from these fluctuations. Okay? And you can look at these fluctuations in the Fourier domain. And, you can see Planck, allowed measurements with amazing accuracy. I should tell you that these are data points, put with error bars, but the error bars are so small that you can see them. So you have to subtract out the best fit model to see the error bars here, right? And it has allowed you to infer cosmology, because what you do is now look at possible cosmological models and search for the model that best fits this very constrained data set. And we now have a very robust understanding then of various parameters in the universe, like how much of it is made of atomic matter, how much of it is made of what is called dark matter, and various other parameters, the expansion rate. And these are known now to accuracies which you see in other branches of physics, like this 1%. This H0 is 1.3%. When I started research in 1990, this was known to a factor of 2. Okay, and similarly, many of these were really uncertain to a big extent. So now we have a model which is very well constrained by observations, and that is called a flat lambda CDM model. Okay, I'll not get into it, but except for the fact that's amazing that everything that we see in the microwave background sky, you can imagine the resolution of the map and the amount of information can be explained by 6 numbers of this model, right? The universe is encapsulated in 6 numbers. 3 of them here, the paranoid density, cold dark matter, and H0, and few others like amount of dark matter and dark energy. So we end up with a very simple model which already gives you amazing a universe to study. And this whole idea of taking this model and the data from Planck, verifying all the theoretical ideas that were behind the predictions for these structures arising from cosmic microwave background, led to the Nobel Prize in 2019 being given to Jim Peebles. Okay, so you count, there are 3 Nobel Prizes now to this field. First was for the first discovery of cosmic microwave background. In 75, Penzias and Wilson were awarded that. In 2006, Obi was awarded a Nobel Prize for the first discovery of fluctuations in the microwave background. And Jim Peebles was awarded the Nobel Prize for the whole picture coming together after the Planck announced its results. And it is, although it's built on a very simple framework, it's an exotic model. We don't know what the 90% of the energy density of the universe is. We only recognize the 5% of it as atomic matter that we have worked with, and high energy physicists have seen various particles, but they all form a part of that 5%. The 95% has a fraction which is dark matter because it clusters. So we call it matter because it clusters like the normal matter. But it has no interaction with electromagnetic light, so we cannot see it directly. It does not absorb or emit light, but we infer it through its gravitational effect. Then there is, even more surprisingly, a large fraction of the universe energy density is made up of something which is an exotic fluid or a new fundamental constant called the cosmological constant, which Einstein had in his basic equations of general relativity. But it was ignored, but it seems to be there now. It corresponds to having some smooth energy density which does not cluster under gravity. It acts repulsively. It's very different from what we understand how gravity works. So there is definitely something more to these are areas where cosmologists have to make progress to understand what is cold dark matter, what is the origin of dark energy, or understand the cosmological constant as a fundamental constant. But remember, the whole inference was made in terms of the perturbed universe. So something perturbing the plasma surface. And we don't also know what did that. And that definitely is some ultra high energy physics and possibly fundamental physics that is responsible for generating the primordial perturbations and stretching the cosmos to be this flat universe. So the story is, with our current observations, we understand the universe and its history based on lab physics up to the first 10 to the power minus 16th second. So somewhere here. Everything that we have inferred is based on basic physics applied to this expanding universe. And we are very confident about it because the observations such as Planck have really nailed the details of the universe and its evolution in this period. What we don't understand is this tiny bit at the beginning, where we believe is hidden this mechanism which has generated the perturbations that we see, which has seeded all the galaxies. So who stretched and pinged the cosmic drum? If you think of the fabric which is expanding as a drum, then there was something which has created these ripples. And the question is what? So as I said, cosmology has been extremely successful because it has been able to link the perturbations that you see when the universe was only 400,000, half a million years old roughly, to a universe which is about 14 billion years old now. So that is the success in getting those numbers to such accuracy. But we still have a huge story to tell and observationally verify what is happening here. What gave rise to these fluctuations that we are seeing in this microwave background, in this cosmic screen, the plasma screen that I'm talking about. And we have a very, very amazing hypothesis or paradigm under which we work. We believe that these fluctuations originated from quantum fluctuations during an epoch of very rapid expansion of the universe. And for various reasons, we believe it happened. And it is amazing then that all that we see in the universe, everything that we see in the universe originated from quantum fluctuations. Okay, and it's a mind-boggling idea. We know that in the current, emphasis on quantum technology, quantum science, but we are making a statement that everything in the universe has a quantum origin. Okay. And the most important part is if that happened, then this must have left a signal in a form of primordial gravitational waves. And that is a signal that can be extracted from more sensitive measurements of the cosmic microwave background. And an aspect of that I didn't touch upon, the cosmic microwave background is polarized. And so any direction you look, there is also there's an intensity fluctuation, but there's also a net linear polarization pattern. So you can put a stick at every point in the sky, and that distribution of sticks tells you the velocity field of the plasma at that time, and also tells you if there was gravitational waves from the early universe which has affected the plasma. At this point, we know that that must have been generated at some level. What we don't know is how strong it is relative to the density perturbations that we have already measured. And that number is just labeled as some ratio called R. And that's very vital because if we know, the day we know R, or we measure the gravity wave background and we have a number for R, we would know the energy scale of inflation. We would know what energy scale did this high energy physics operate at. And one of the guesses is that it must be related to the energy scale at which grand unified theory happened, where all the forces of nature were unified. So imagine with a satellite, we would be able to make inferences so deep and so important about the fundamental laws of nature. Currently, we haven't detected this, and there's only an upper limit, which is getting stronger and stronger as experiments probe the sky. But this is a must-do for cosmology, and cosmological community is going for it. So we are looking at a project which we have, sort of proposed to ISRO, which is called CMB Bhārat satellite. As I told you, it has a promise for a path-breaking science, but in doing so, it will also produce a lot of high-value science and also a legacy of lot of astrophysical data, which will, keep astronomers busy for decades. On the technology side, if we go for something, we would be seeding technology frontier programs related to capabilities in space technology, promoting nascent technology in the Indian labs, and it also has challenges for the science mission that needs to be done because it has to operate from L2, which is something that ISRO has yet to touch. And of course, then there is high performance computing, IT, big data, all that. So there's a lot of breadth and a pinnacle to a very, very important result. So what does the CMB satellite look like? Okay, this is a sketch that we have produced from the proposal document. So it's a satellite which looks at the incoming CMB radiation, has a primary mirror, in fact, a system of 3 mirrors, which then finally gets the radiation to a focal plane, which has to be cryogenically cooled. And so it has to be a cryogenic mission where you achieve 0.1 Kelvin, 100 millikelvin kind of temperature on the at this point. And remember, as spacecraft people, you would know that this blue line is a sunscreen, and there would be solar panels right here, which will be heated to 300 Kelvin. And in the same spacecraft, you have a surface which is at 300 Kelvin and area which is maintained as 0.1 microkelvin. Okay, so this, I won't get into what the specs of this mission. It is be measuring in what you call the terahertz detector range. So somewhere between 60 to 1000 gigahertz range in multiple channels. There are about 20 plus channels. And it will be at unprecedented sensitivity, accuracy, and angular resolution. Okay, so this is a chart of the spacecraft specifications with very detailed things which we put out in our proposal. You can see that we really worked hard on it. So we have details that are at very mature level. And if people are interested, I could even talk about the TRLs of various things. But let me just talk about the key features of this mission. Okay, so there are technical contributions that are challenging: mission planning and operations, launch to L2 tracking. Another big challenge is the thermal infrastructure. So you have to have a solar shield, but then very interesting hot and separation of the hot cold stage, which was achieved in Planck by a V groove separator and thermal design. And then, of course, the service modules and all these things. And then telescope optics, reflector, baffles, reimaging telescopes. And, I've just pointed to possible places in ISRO where there are expertise already. There's also the thermal system, as I said, which leads to the primary stages of the cooler in the cryogenic chain, which obviously we have already got. So this, for example, is a layout of the silicon carbide telescope optics that is proposed here. This is certainly in line with the goals of ISRO in developing silicon carbide optics mirrors. Some little things from the DOS website to show that we are on the way to developing the technology. And then for engineers, there's this big challenge of separating the temperature at 300 Kelvin here to this shielded area where it has to be 40 Kelvin. And then there will be active coolers which will cool the detector to 100 microkelvins. 100 millikelvin, sorry. So this is the layout of, very schematic layout of the thing, there's a part which is the first stage of the cryogenics here, then it feeds into this through this V groove into this area which is at 40 Kelvin, and then this is the detector plane which is at 100 millikelvin. Okay, and these are the components, right? And many of them are probably things that we need to develop or learn where to do it, how to do it. Then, of course, there are photon noise limited sensors and readouts, and which expertise exists in the international community, but the cryogenic coolers are 100 millikelvins in space. These are things that will be the new aspects that Indian space would be exposed to in taking up a challenge like this. It is not totally uncharted territory. The Planck satellite, which I showed you how successful it was, did most of it. It had this cryogenic, focal plane. It had the V groove separators, which separated the hot phase from this cold optics here. So the mirrors have to be at 40 kelvins, right? So this is a solved problem. It did go to L2 and deliver data, but its detectors were not sensitive enough. So to get to our goal, we have to have a polarized detector channels with an array of bolometers, polarized bolometers, which are maintained at hypermech 100 millikelvin. Each of these bolometers is capable of measuring power at attowatts. Okay, attowatts of power, considerably improving over the sensitivity that we have. So this is a more ambitious focal plane with more capable detectors and more larger number of them. And I'll leave these details out. But there is technology which exists, which are mature enough now and deployed on ground to be, probably flown to space. As I said, there are TRL levels around the world. In India, this development is yet to happen, but at Raman Research Institute, I very much expect to start an activity where we get expert faculty members who are experts in this terahertz detector design and science with them, right? So right out of the teams from Caltech. So these are pictures which would be possibly, so there's two broad things. One is this kinetic inductance detectors, MKIDs, and then there is also this other thing, which are transition edge superconducting bolometers. And this is actually a picture from a tile of such bolometers, which have been deployed in a ground station in something called the Siemens Observatory, which is in Chile. Okay. And then, there are phased antenna designs, which are already mature, but, things that we can improve on and, adopt for this thing or, exchange in international collaboration. So this would require building upon the capabilities in ISRO and enhance the experimental physics effort and the academic institutions in India. Nanofabrication of such MEMS and cryogenic capabilities, all these would bring in huge high-tech gains to the country. And quantum sensor technologies not only would benefit space probes. Terahertz technology has many other applications other than looking at the microwave background. You can look back at the ground also with the same detectors. And this whole technology can be extended to other bands of astronomy and, as I said, other areas of interest. So I wanted to present this as a possibility that we put forward, which could be an ISRO-led mission with substantial European participation, or also NASA participation, and various ways that we can make it happen, After we put up the proposal, it has been discussed. I have met some of you I have been to Space Application Center, LEOS, among other places to discuss this proposal and the technology benefits. There was a committee set up to study that. I think the pandemic interrupted our meetings, so I don't know where it stands. But I believe that this is a very exciting project to keep in mind for ISRO people, because I think as engineers, we stand to make the grandest contributions here in taking this forward. Okay, so we had various meetings, as I said, at various stages, and we have also had meetings on this technology dividends of CMB Bhārat, and so I soon expect that something like this may come up, and that would involve a lot of scientists also in various working groups. And we have already got the science work done. We are publishing papers on the science goal, meanwhile keeping an eye on how we find ISRO response to it. So I would like to end here with the statement that we know cosmology made a huge leap with the launch of the most recent CMB mission, which was launched now more than a decade back. This was the Planck launch from Kourou, and on an Ariane rocket. I really fondly hope that something like CMB Bharat will be launched by ISRO in its most capable spacecraft, the GSLV Mark III, sometime in the future. Thank you.
Thank you so much, sir, for this beautiful talk. In fact, you kept your time to the mark. Now I request Dr. Girish Sharma to handle the question answer session. Dr. Girish Sharma.
Tarun, for a very.
Sir, kindly unmute yourself, sir.
I am unmuted. Can you hear?
Yeah, you're little louder, sir.
Hello.
Yes.
Thank you, Dr. Tarun, for delivering a very exciting topic on the National Science Day. Actually, here we designate ourselves as a scientist / engineer. Really, today's speaker is an engineer, mechanical engineer with a passion for science. Then he has changed his engineering field to the scientific domain of cosmic origin and all those subjects. Now again, he has put forth a very complex engineering problem in front of ISRO to develop a very complex spacecraft. So I think we started the session with from the darkness and taken a very small glow of light. Maybe we have gone back to some 13 billion years ago. He has taken us, and how the universe has started from its very hot stage to expanding cold stage. So the space-time expansion also he has explained very nicely, and the fluctuations, how complex the fluctuations and how sensitive that fluctuations and the required instrumentation to capture that fluctuations. All those complex problems he has shared with us, and hope this project of CMB Bharat will give a lot of challenges to the engineers in ISRO, as well as a very useful information to the scientific community who is looking forward to find the origin of the universe and its complex nature for the future generations to understand. Now the question answer session we can go. I think let me start with a very simple and layman's question. Sir, how do we compare the contribution of recently flown James Webb in finding out this space-time expansion relationship in its infrared wavelength.
So James Webb Telescope is still making its way to L2, second Lagrange point. It has not started observations yet. But soon they will start opening up some of their things for, tests, engineering tests. Then, so it is going to peer back to a universe, but not too far. It will allow us to see the universe. I showed you these galaxies, Hubble, where you saw galaxies which
Yeah.
are just forming. It is that epoch it can see much more clearly because it has that infrared capability.
Yeah.
Okay, and it will be able to see the first structures forming in the universe. And that is of enormous importance because that there are complementary probes. And I should be proudly saying that today you would see there's a press release from Raman Research Institute on a complementary approach to see that same epoch, but in neutral hydrogen. The complement to the structures that are formed, there is also a signal in the rest of the matter, which is yet to coalesce into galaxies and called the epoch of reionization. That is what James Webb will peer back to. But that would be more like a universe which is, a young man compared to a 100-year-old man. The cosmic macro background goes to a 1-day-old universe.
Yeah.
Right. So James Webb will make enormous contributions to understanding the universe relative to what we're looking at relatively recent past. But this, in human timescales is already billions of years.
Yeah. Participants now can ask questions and have a discussion on this interesting topic. Please come forward. Hello.
Sir, good evening, sir. Rajashekar once again. Suppose if you are planning next modern COBE satellite as a space probe, where it will be positioned, either it will be in Earth orbit or it has to go to L2.
It has to be in L2. So
Okay.
this is the modern COBE satellite.
Okay, sir.
Because COBE was superseded by the WMAP satellite, and then that was superseded in capability by the Planck surveyor from ESA. COBE and WMAP were both NASA missions, and after Planck, we very much expected next generation satellite to be funded. But you should realize that now technology required for such a satellite and the cost of such a satellite is so large that it cannot be a single agency doing it. Because no single country has the resources, manpower, as well as the technology.
Yeah.
So even if a satellite like this was built by ESA, maybe the detectors would come from US, from NASA, and already there is a possible satellite, but with much lesser capability, being proposed by Japan in collaboration with ESA and NASA, called Lightbird. In this same, but it targets only the gravity wave signal. But I think the community is not very sure whether it will be able to get to the priced goal that we are looking for. But nevertheless, that is already a way forward, that there is a satellite which, at least from the JAXA side, they have a go ahead. But I don't think the European participation is yet completely clear. But that is an exciting area. So these are essentially next generation, and they will all be at L2 because you have to be away from the sun and any contaminating radiation and cold, stable environment.
Thank you, sir. Actually, I have read the book Wrinkles in Time by George Smoot. Subsequently, after I read that book, the next year he got a Nobel.
Right.
Probably, I request you to write a book on this to the popular audience. Okay. Wish you all the best, sir.
Thank you so much.
Yes, sir.
Participants
So
may
you had
ask.
been mentioning about a cryogenic temperature for the detectors. What was the temperature level that you had been talking about? I heard
100 millikelvin.
100
It's 0.1 Kelvin above 0.
1 Kelvin. And
0.1, 1/10 of a Kelvin.
1/10 of a Kelvin. That today, who all have that technology?
No, so the
readiness for that?
Planck had the ability to cool it to few.
Planck had, I think, 4 Kelvin, no?
4 Kelvin, yes.
4
But
Kelvin.
now we have to go to
Of a
0.1 Kelvin.
It's far
Such
away.
cryogenic coolers have been already designed.
Yeah.
These one other problem with Planck was that it was venting out the helium. So then the lifetime of the project was determined by how much helium it could carry, cryogen it could carry. So it could measure run that a part of the experiment for only 2.5 years. But that was good enough. We got 5 passes of the sky, and the results you see here. But now we are looking at these cryogenic refrigerators with closed cycle, so that we don't lose the cryogen. And these are being developed. Of course, such things are easier to develop on the ground, much easier, because there are many cryogenic facilities at the temperature we're talking about on the ground. But doing it in space in the limited volume that you have and the robustness you require, because you can't switch on, switch off, you can't do anything, is a challenge. But I think the technology is pretty high level. So let's review that. So okay, I don't probably have the active cooling. It's a fairly high TRL level, right? 5 if we don't want to lose cryogens, and 7 and 8 if we are okay with this, ADR pulse thing and Joule Thomson. So these are,
thank you.
Yeah, this is the closed cycle one is at level 5, and this one is at level 7, 8.
Any question from participant side? Hello. I think there are no questions in the chat box also.
Okay.
Can we conclude, Senthil? No?
Yes, sir. Yes, sir. You may please proceed with the vote of thanks. I believe there are no more questions. If any member has a question, you can please post it on the chat box. We'll get it from Dr. Tarun sir later.
Yeah, and also my email ID is tarun@rri.s.in. I am in town now in Bangalore, so where a lot of the ISRO people are. But I have visited SAC many times, not VSSC yet, but IIST in Trivandrum. And I would really, really look forward to any interactions that you would like to have with me or my team members on this project.
Yeah, definitely, sir. We have to, because it's a very complex project also for us also to take up. So it's very interesting requirements. I think we started from the fundamental cosmic science, and finally comes to as a project report on ISRO.
Right.
Anyway, on behalf of C, I would like to express my sincere thanks to Dr. Tarun for delivering a very exciting talk, and kept this session very interactive with the queries. And our special thanks to our senior most C members, because they have been encouraging all along our Space Engineers Association activities. And I would like to mention the efforts of C Executive Committee, especially my co-members in the Technical Board, Sri Rajashekhar, Dr. Pankaj, Sri Ramaswamy and Santosh Kumar, for arranging this talk in a very relevant day of National Science Day. I would like to thank our C President Sri Satish Kumar, Vice Presidents Dr. Arumugham, Dr. Mohan Kumar and Jayanti Madam, and our special thanks to our General Secretary also. I would like to express my sincere gratitude to all the participants which they have been listening patiently throughout our 1 hour discussion on this particular topic. I think with this regular webinars are going on, because of these participants and good speakers, it's a very good support for the committee to go ahead with more and more webinars on the different topics of the interest and topic of the day. I would like to hand over General Secretary to officially conclude this session. Thank you, sir.
Thank you, Dr. Giri sir. That was a very nice way of concluding the session. So on behalf of the whole of space engineers from ISRO, I would again place on record our heartiest thanks to Dr. Tarun Souradeep from Raman Research Institute. He was very forthcoming. The first message that I requested him, sir, on National Science Day, we would like to have your talk. He was immediately forthcoming and said he's very ready to give a talk. He needed only 1 week time to propose the title for this. And today he has kept his time so perfectly within 45 minutes. And then of course 15 minutes for our discussion. So sir, thank you so much for sparing us your time for today.
Thank you. The pleasure was entirely mine.
We'll surely be in touch with you, sir. Any of us who have come, who will be interested in this project, any information comes to us, we'll be directing them to you, and so that we can probably more discussion can happen in this way.
Thank you. I appreciate that.
Thank you, sir. So any of your instrument development projects and all, you can feel free to communicate to us, sir. We are ready to help you.
Thank you so much. Yeah, it would really help, because there is of course a formal way in which this project happens, but from my LIGO India experience, we actually talk directly to the engineers at Raman, at the Center for Advanced Technology and Institute for Plasma
whatever
Research.
may be your requirement, we are ready to help you. Okay.
Thank you so much. Thank you so much.
Thank you, sir. Nice of you.
Thank you.
Thank you.
Thank you so much, sir. We have come to the end of the session. So good evening to all of you.
Okay.
Thank you.
Good night.
Thank you.
Okay, so I'll close the thing.
Okay, thank you.
Thank you, Sandra.
Giri sir, thank you, sir. Thank you so much.
Okay, thank you. Good night.
Okay, sir. Good night, sir. Dr. Karthikeyan, good evening.
Thank you, sir. Thank you.